This is video 45 in the lectures on the design of reinforced beams. This lecture deals with 3 examples or exercises for pre-stressed concrete. This is example 1. An isostatic beam of 15 meters is loaded with a uniform distributed load of 12 kN per meter in characteristic, serviceability, limit state characteristic. The initial pre-stress force is 1100 kN. The eccentricity is constant over the span and is 325 millimeters. The pre-stress losses in short term are 6% and in long term 20%, but in that 20% is inclusive the short term losses. We will calculate the stresses in the extreme fibers of the cross section, and this for the cross section at midspan. And we will consider 2 load cases. Load case 1 is only the proper weight plus short-term losses. That is at the start when the tendons are put under stress. And then we will see on the long term the load case 2, which is the total load plus the long-term losses. So this is short-term, long-term. The concrete area is then equal to 237,500. When you have an eye profile, sometimes it's very easy just to use the subtraction rule. The W is E over V accent or E over V is then equal, again, we are using the subtraction rule to calculate the moment of inertia. And V or V accent is 750, the total height divided by, or the total depth divided by 2. The bending moment due to the proper weight is just the cross section of the beam multiplied by 25 and then times 15 squared divided by 8 is 167 kilonewton meter. The total bending moment, it's the proper weight bending moment plus the proper weight plus the total load, the serviceability load of 12 kilonewton per meter times 15 squared over 8 gives you 504.5 kilonewton meter. Now we will look at load case 1, which is the short term. We look at a top fiber. In the top fiber, we know that we have the summation of 3 stresses, the stresses of the top fiber, which is one for the pre-stress, the other is for the bending moment caused by the pre-stress, and the other one is for the proper weight of the beam. We are now looking at the top fiber, so it means that we take the minimum pre-stressing force and the minimum load. We know that the losses are 6%, so we take 0.94 times the pre-stress force, 1100, divided by AC, what we just calculated. The bending moment caused by the pre-stressing force is P times E, but it's eta P because it's with the 6% losses inclusive. And then the proper weight. And then we have in total of plus 0.26 megapascal, and the plus sign means tension. So the top fiber in short term, just after releasing the pre-stressing force, the top fiber is in tension. The bottom fiber is the same equation, but now we change signs for those two. And when we recalculate it, we have minus 8.96, let's say 9 megapascal, but compression. So the top fiber is in tension and the bottom fiber is in compression, of course, because the tendon is at near the bottom side. For load case 2, long term, the top fiber now is given by this equation. And it gives us almost 10 megapascal in compression, and the bottom fiber again, we switch sign, equals now 2.25 megapascal, which is in tension. So if you look at load case 1, at the stress diagram, you see that we have a very small amount of tension on top and a big one on compression on the bottom. This is when the tension reinforcement, when the pre-stressed force is applied, you have of course a big compressive force at the bottom, and this is under, at long term, under the load, under the maximum load. We have then large compression on top and a small tension stress on the bottom. So the first example was to show you how you calculate in certain sections or certain loads, how you can calculate the stresses. Then in a second example, we have an isostatic beam. It's the same beam of 50 meter span. It's loaded with uniform distribution load of 12 kilonewton per meter. Eccentricity is 325. Again, short-term loss is 6%, long-term 20%. And now we need to calculate the needed pre-stress, causing no tensile stress in the extreme fiber of the cross-section at mid-span. So instead of that, the pre-stress is given and we are checking the stresses. Now the pre-stress is not given. We have to design the pre-stress in such a way that for the cross-section at mid-span, there is no tension stress in the extreme fiber. And we will consider two load cases, again, short-term and long-term. We have the area of the cross-section of the concrete. We have the W, the bending moment under proper weight, and the total bending moment. And we have seen from example S1, that's why we have done this example, that tension is only expected in the top fiber at load case 1 and the bottom fiber at load case 2. So because we know that now, because we are a little bit experienced, we will instead of checking the 4 situations, we will only check the tension in the top fiber and in load case 1 and the tension in the bottom fiber at load case 2. So top fiber, load case 1, we do not have P, we don't know what the pre-stressing force is, so it stays in the equation, but we know that we do not want any tension in the top fiber. That was the goal, so it means that it must be negative, so it must be smaller than 0, and this gives you a value for P. That means that the pre-stressing force must be smaller than 1041 kilonewton. If not, if this is bigger than 1041, the top fiber will be under stress, under tensile stress. In load case 2, the bottom fiber, we use the formula, we calculate it in function of P, and we see again that the bottom fiber may not be in tension, so it must be smaller, it must be negative, smaller than 0. So P now must be bigger than 1316 kilonewton. So on the long term, for the bottom fiber not to have tension, the pre-stressing force must be bigger than 1316 kilonewton. Now we have a problem, because those two conditions cannot be true at the same time. You cannot be a pre-stressing force smaller than 1000 and bigger than 1300. So we have now a problem. We must make a proper choice, and we do that by stating that the long-term condition is dominant, not the short-term condition. So because LC1 is a temporary situation, we choose for pre-stress equal to 1316. Then we have an example 3. Again, same isostatic beam with a span of 15 meters, an initial pre-stressing force of 1100 kilonewton and an eccentricity of 325. We will now calculate the equivalent loading system for the pre-stress using a bilinear tendon profile with an inclined section of 2 meters. So the maximum eccentricity is 325, but we will use a bilinear tendon profile. And then after that, we will calculate the equivalent loading system F or the pre-stress using a single radius tendon profile with eccentricity 0 at the supports. So we have now two options. The tendon profile is bilinear or a single radius tendon, and we will see, and we will have to calculate the equivalent forces for those two cases. Let's assume the first case, the bilinear tendon profile with the first 2 meters, it's inclined. The maximum eccentricity is 0.235 meters, and this is then the profile, the tendon profile. Now we are looking for the equivalent forces. So because of symmetry, we know that V1 is equal to V2 and V3 is equal to V4, and R1 is equal to R2. The vertical equilibrium states that the net force must be 0. So R1 plus R2 must be 0, and V1 plus V2 must be equal to V3 plus V4, and this results, of course, that the reactions are 0 and that all forces V1 up to V4 are equal and are equal to V. So this green system of forces is equal to the pre-stressing profile of this beam. So if you calculate, when you calculate now in the load case pre-stressing, you use the green forces. But we still have now to look for or to express what is the value of V. We know they are equal, but what is this value? To do so, we look at the section A, and the bending moment at section A in the beam is, of course, P times the eccentricity, E, P times E. P is the pre-stressing force, and it is also, these are 2 meters, so it is also V, the force V times 2 meters. So the bending moment here in this section equals PE is 2V, or we know that the pre-stressing force is 1100, the eccentricity 0.3225, so we know V is 179 kilonewton. And this is now the total equivalent system. And this system mimics the effect of the pre-tensioning. Now we look at the single radius tendon profile. This is the equivalent forces with Q equals P over R. Now we do the same thing. Because of symmetry, R1 is equal to R2 and V1 is equals to V2. We take a vertical equilibrium. The sum of the two R's is 0, and V1 plus V2 must be equal to Q times L. And this results in that the reaction forces are 0 and that V1 and V2 is equal to V. It's equal to QL over 2 and is equal to PL over 2R. Because Q is P over R. We now still have to calculate the radius, which is L squared over 8E, because the second derivative of the coordinate equals the 1 over the radius, but this is an assumption for small deflections. So it means, in fact, that there is a term E over 2, which is neglected in the calculation of R. But we will use R is L squared over 8E, and it gives us 86.5 meters. And the uniform distributed load is then equals to 12.7 kilonewton per meter. The shear force at the support is then 95 kilonewton, and then we got not the shear force at the support, but the vertical load at the support to make the equilibrium is then 95.33. So this is now the equivalent system of the pre-stressing case. This lecture dealt with 3 examples or exercises for pre-stressed concrete. See you at next lecture.